This video should be short because we're talking about the p-series test, which follows directly from the integral test. Here's what the p-series test says. It says that we're taking the summation from n equals 1 to infinity of 1 over n to the p. And here p is going to be an integer. And specifically for the integer test, p will be greater than 0. P has to be a positive number. If p is a negative number, then what you would do is shift the n to the p up to the top so that p is now a positive number. But anyway, here's what the p-series test says. It says that this integral converges if p is greater than 1, and this series diverges if p is less than or equal to 1. And then holding with this idea here that p is greater than 0, basically if p is between 0 and 1, including 1, then this series diverges. So let's take a look at our celebrity function, the harmonic series. If you recall the harmonic series, you could write it out 1 plus a half plus a third plus a fourth plus blah blah blah. Or we could write it as the summation n equals 1 to infinity of 1 over n. Hey, let's apply the p-series test to this. Notice here that the exponent on the n is a 1. Okay, so therefore p equals 1. Let's go back to the previous slide. Oh hey, p equals 1, therefore this series diverges. That's it, diverges. It's kind of anticlimactic, but that's how you would prove that the harmonic series diverges. A slightly more satisfying way to prove that the harmonic series diverges is to actually do the integral test on it. So let's say that we do the integral from 1 over x from 1 to infinity dx, because remember this is like the summation from n equals 1 to infinity of 1 over n. So here's our harmonic series, and this is the integral representing it. So we're going to integrate this. Well, the integral of 1 over x is natural log, so we have the natural log of absolute value of x evaluated from 1 to infinity. Plugging in the limits, we get ln infinity minus ln of 1. The ln of 1 is 0, and the natural log of infinity is, guess what? Infinity. Therefore, this integral diverges, and because using the integral test, these go hand in hand, this summation will also diverge. So that's another way to prove that the harmonic series diverges. Let's do some quick practice with using the integral test and the p-series test to see how these come up. So let's take a look at this first one. We have 1 over k squared plus 4. Now, we'll learn in a later section how to do what's called the comparison test, but basically it's what does this function kind of look like as k gets really big? And using the ideas from Bobo-Botten or L'Hopital's rule, essentially we can ignore this plus 4, and 1 over k squared plus 4 will just act as 1 over k squared. Oh, this is essentially 1 over n to the p, and here the power is 2. Therefore, because 2 is bigger than 1, this series converges. Alright, let's go to the next one. We have n over n plus 1. Now if you use the nth term test, notice that the ratio here does not go to 0, right? N over n is going to be 1, and so because the limit of these terms is 1 and not 0, this will diverge because of the nth term test. Coming to the next one, 1 over n square root of n. Sometimes things are going to be written strangely, but try to simplify them before you do anything, especially if there's no addition or subtraction. So here we have 1 over n to the first times n to the 1/2. Oh, we can combine these exponents by adding them, and so we'll get n to the 3/2. Do you see that? That's the power. This is a p-series, it's a power series, and because p is 3/2, which is bigger than 1, this will converge. Notice that we haven't actually had to do any integrals, which is nice. However, that's going to change in the next example. In this example, we can't do the p-series test because there is no, you can't use the p-test if you have things that are not polynomials. ln of n is not a polynomial, therefore you can't use the p-series test. So let's take a look at what to do. Do you see a function and its derivative? Let's try to use the integral test. So if I try to integrate 1 over x ln x dx, Well, we're going to have a u substitution because u is going to be ln x, and so the du will be 1 over x dx. I don't need to doctor counterbalance, and notice here this is that 1 over x that we were looking for the du. So when I rewrite this, I will have the integral of 1 over u du, and then plugging, and this integral is natural log, so I'll get ln, absolute value. Oh, the u was ln, so I'm going to plug that back in. And then no plus c, but I'm going to evaluate this from our limits, which go from 1 to infinity, 1 to infinity, and then I plug them in. If I plug in infinity into ln of x, I get ln of infinity, which is infinite. And then I take the natural log of infinity again, and so I get infinity. Interesting. So therefore, because of the integral test, this series up here will diverge. So a lot of sequences in series is going to be picking the right test to do. Oftentimes you can get, like, I would always start with the nth term test, and then I would either branch off into a p-series, try to identify what kind of series it is. Is it a p-series, or is it geometric, or can you integrate it? And those are the tests that we've learned so far, and we'll learn some more, but for now, just those are the main things, the main tools that you're going to use to determine if a series converges or diverges.